Am I audible? Okay. As most of the topics are completed, we'll discuss the today we'll discuss the stability of the beams. Okay, statistical analysis of determinate beams. The study about the determinate beams. Ask your friends to join the class. I'm sharing the screen. Okay, let me know if it is visible or not.
Structural analysis. Statically determinate beams. In this lecture, we are going to answer two questions. What is a statically determinate beam, and how to analyze it? A beam is a properly supported structural member capable of carrying loads that are
The syllabus is almost over. I'm discussing again all the methods we have discussed so far. Okay, like it will be revision from the start. So if you have confusion, clear your doubts here itself, or you can contact personally. Ask your friends to join the class. Only 18. Let's wait for 1 or 2 minutes. Okay, let's start the class. Audio and video is okay, right?
Structural analysis. Statically determinate beams. In this lecture, we are going to answer two questions. What is a statically determinate beam and how to analyze it? A beam is a properly supported structural member capable of carrying loads that are perpendicular. Structural analysis. Statically determinate beams. In this lecture, we are going to answer two questions. What is a statically determinate beam and how to analyze it? A beam is a properly supported structural member capable of carrying loads that are perpendicular to its longitudinal axis. Such a member is called a beam because the loads cause it to bend, like this. The analysis of such a beam involves calculating its support reactions. In this example, beam analysis entails calculating the three support reactions, AX, AY, and BY. Then, what is a statically determinate beam? A beam is called statically determinate if its unknown reactions can be calculated solely using the equilibrium equations. Now, how do we analyze such a beam? Before we can answer the question, let's review reaction forces associated with each type of support. The three most common support types are pin, roller, and fixed supports. There are two reactions.
So pin support is represented by this symbol, roller is represented by this symbol, and fixed is represented by this symbol. Okay, so you should know what will be the reactions for this support, what will be the reaction for roller support, and what will be the reactions for fixed support. So please remember these symbols, okay, for different types of supports.
Forces associated with a pin support, a force in the x direction and one in the y direction. A roller support provides one reaction force only. Here, the force is perpendicular to the support surface. A fixed support has three reactions, a force in the x direction, a force in the y direction, and a bending moment about the z.
Your pin support will have two reaction, Fx and Fy. Okay, and your roller support will have only reaction only in this direction, vertical. And your fixed support will have that it will have reaction in both horizontal and vertical. Along with it will create a movement. Okay, this is your movement, and it will resist your this fixed position will resist your horizontal movement, your vertical movement, and it will restrict your movement, this movement also, clockwise or anti-clockwise. But your this roller support will only resist your vertical movement, and pin support will resist your vertical and horizontal movement. Okay, horizontal movement is represented by Fx, and vertical movement is represented by your Fy. Okay.
Axis. To clarify, let's look at two examples. Suppose our beam has a pin support and a roller support. Here, there are three reaction forces. Two forces associated with the pin
So
support.
if a beam is given with one pin joint and one roller, so these will be your reactions. Okay.
And one force associated with the roller
External
support.
reactions.
In this example, the beam is fixed at one end, but free at the other end. Therefore, there are three reactions involved here.
So this is a simple frame, or you can say beam, which is vertically fixed at this position. So it will have three reactions: vertical, horizontal, and moment.
Force in the x direction, a force in the y direction, and a bending moment. In order to analyze a beam, it is customary to draw a diagram called the free body diagram, showing the applied and reaction forces and their locations in a Cartesian coordinate system. Note how each unknown force in the diagram has been uniquely labeled. The free body diagram helps.
So this is a simply supported beam with one side of the beam is supported at pin joint and another side is supported at roller joint, and these are the reactions. A single load is applied on the beam at a distance of L by 2 from both the supports. Okay.
with the correct formulation of the equilibrium equations. To determine the support reactions, that is, to analyze the beam, we use three equations. 1. Sum of the forces in the x direction must be 0. 2. Sum of the forces in the y direction must be 0. 3. Sum of the moments about the z-axis.
So we'll use three equilibrium equations, which is summation of all the horizontal forces equals to 0, summation of all the vertical forces equals to 0, and summation of moments about a particular point equals to 0. So this is also called as static equilibrium equation, and these are the three equations which we use to find out the reactions. Okay.
At, say, point A must be 0. The first equation in the expanded form gives us AX equals 0. The second equation gives us AY plus BY minus P equals 0. Third equation gives us P times L divided by 2 minus BY times L equals 0.
So if you see, if I equate all the horizontal forces equals to 0, so what are the horizontal forces acting on this beam? Only Ax, right? So it will be Ax equals to 0. And if I sum up all the vertical forces, so vertical forces is my Ay, By, and this P. So these are in upward directions, and this is in negative downward direction. So I'm considering upward forces. I'm considering upward forces as positive and downward forces as negative. So summation. So Ay, By will be positive, and this P will be, as this is downward, so it is negative. Summation is 0. Okay. Now let's move to the moment. So I'm taking all the moments about a point A. So what is the formula for moment? It will be your force into distance, right? Moment is your force into distance. So I'm taking all the moments about a point A 0. So let's start with this reactions, which is By. So this is the By is your force, and By is acting at the distance of the L length, right? So this L will be my length, and the force will be your By. So By into L. As this is anti-clockwise direction, I'm taking anti-clockwise as negative and clockwise as positive. So this By force is acting anti-clockwise, so it will be minus By into L. And this P will create a clockwise movement. That's why this is of P is the force, and it is acting at a distance of L by 2. So it will be P into L by 2. So this is the clockwise direction. So positive movement, minus this is anti-clockwise direction. So this is the negative movement. Okay, we'll solve this and we'll find the reactions on this beam.
Solving the third equation for By gives us By equals P divided by 2. Solving the second equation for Ay gives Ay equals P divided by 2.
So I got Ay and By is P by 2.
Before we end this session, let's look at two more examples. Here, we have a cantilever beam subjected to a uniformly distributed load.
So this is
Let's
a
analyze the beam.
cantilever beam. Okay, I'm not discussing the types of beam and types of load. That is very easy, and if you have any confusion, go back to previous classes videos. Okay, so this is a cantilever beam, and the load is a type of load is your UDL, uniformly distributed load. So 2 Newton per meter is uniformly distributed over a 10-meter span beam, and cantilever beam is used to be fixed at one position, another and used to be free, right? So recall all previous classes. So let's start with this.
First, we draw the free body diagram for the beam. For the purpose of finding the support reactions, we can replace the uniformly distributed load with its equivalent concentrated load. Now we can write the equilibrium equations. AX equals 0. AY minus 20 equals 0. MA minus 20 times 5 equals 0.
Again, I'm using
Solving the
equilibrium
last equation
equations
for
to
MA
find out
gives
the reactions
MA equals 100. From the second equation, we get AY
and
equals
moments.
20.
So by using
And the first
equilibrium equations,
equation
I got
gives
movement
us
of 100 Newton
AX
meter
equals 0.
and reaction of 20 Newton at AY. So please
The second example is a
see the
beam with
units.
a
Okay,
pin
units play
support
important
at the
role.
left end, a roller support at the right end, and another roller support at the middle of the beam. The beam is subjected to two concentrated loads. To analyze the beam, we start by drawing
So this
its
is a
free
simply
body
supported beam
diagram.
with three supports, one pin and other two are roller, and two loads are applied of P and P. For AB span, it is also called as continuous beam. Okay, there are more than two supports, so it is also a continuous type of beam. Okay, let's see how to solve for this.
Note that the diagram shows four unknown forces, two support reactions for the pin support, and one reaction for each of the roller supports. Here, the equilibrium equations are AX equals 0, AY plus BY plus CY minus 2 times P equals 0. 5 times P plus 15 times P minus 20 times CY minus 10 times BY equals 0. Notice that we have four unknowns, but only three equations. Therefore, we cannot solve for the unknowns. The beam is not statically determinate. We will discuss techniques for...
So see, three equations. Here we have only three equations, and the unknowns are four unknowns, right? So statically, this will be your statically indeterminate beam because you cannot solve for the unknowns. When there will be more unknowns comparison to your equations, you cannot determine those reactions, and it is called as statically indeterminate beams. Okay, if you in earlier problems we saw that those three equations were sufficient to find out the reactions, so it was called as it is called as statically determinate beams. So when these reactions are insufficient to find these unknowns, or you can say when the number of unknowns is more comparison to the equations, your beam is called as statically indeterminate beams. There is another way to solve these problems. Okay, so just to categorize these two, you should know that your number of unknowns should be less or equal to the number of equations. Okay, that is the difference between statically determinate and indeterminate beams.
analyzing statically indeterminate beams later in the course.
So hope this part is clear. Any confusion from this part? You can type in the chat box any confusion in this part. Okay, let's move to the another part. Stability of the structure.
In this session, I'm going to talk about stability of structures. A structural system, be
Is
it a
audio
beam,
video okay?
Yes, ma'am.
Okay.
in this session, I'm going to talk about stability of structures. A structural system, be it a beam, a truss, or a frame, can be viewed as a rigid body that is properly restrained by one or more supports.
So for the stability of beam, truss or frame, let's see.
Such a system is said to be externally stable if it does not undergo any rigid body motion, regardless of the position of the applied loads. Consider a simple frame structure supported by two rollers. If we apply a horizontal load to the frame, it starts rolling horizontally on the support surface. The structure undergoes rigid body motion. Therefore, the frame is said to be externally unstable. If, however, we replaced one of the rollers with a pin support, the structure becomes externally stable, as the pin prevents the rolling of the frame on the support surface. Let's consider another example. Here, we have a truss structure that rests on two supports, a pin and a roller. Clearly, the supports prevent any rigid body movement of the entire structure. Yet, the truss is considered to be unstable. Why? Because here, we have localized rigid body motion. Some of the truss members are not properly restrained. They can have limited free movement. This is called internal instability. A structure is said to be stable if and only if it is neither externally nor internally unstable. To determine if a structure is stable, we need to ask three questions. 1. Does there exist a loading pattern that makes equation sum of the forces in the x direction equals 0 unsatisfiable? 2. Does there exist a loading pattern that makes equation sum of the forces in the y direction equals 0 unsatisfiable? 3. Does there exist a loading pattern that makes equation sum of the moments about the z-axis equals 0 unsatisfiable? If the answer to any of these questions is yes, then the structure is considered unstable. Consider a simple beam resting on two rollers. Here, equation sum of the forces in the x direction equals 0 cannot be satisfied if a non-zero force is placed on the beam. Why? Because summing the forces in the x direction gives us P. Since P is not 0, then the sum cannot be 0. This implies the structure is unstable. Here's another example. The structure is supported by a pin at A and a roller at B. The free body diagram for the structure shows three reaction forces all passing through point A. If a non-zero vertical force P is placed at the midpoint of member AB, then the sum of the moments about point A becomes P times L over 2. Since neither P nor L is 0, then the sum is not 0. This means the structure is unstable. Let's look at one more beam example. This beam has three reaction forces. Note how all of them pass through a single point, point D. If we subject the beam to a non-zero vertical force P at, say, point A, the moment equilibrium equation becomes P times L. Since this product is not 0, the equation is not satisfied. Therefore, the structure is not stable. Now, let's turn our attention to internal stability of structures. The discussion generally comes up when dealing with trusses. Assuming a truss is externally stable, we can determine its internal stability in one of two ways. The simplest way is to compare the number of equilibrium equations to the number of unknowns for the truss. If the number of equations exceeds the number of unknowns, the structure is considered unstable. Here is an example. This truss has 6 joints and 8 members. Since the number of equilibrium equations for a truss equals 2 times the number of its joints, we get 2 times 6, or 12 equilibrium equations. The number of unknown forces equals to the number of truss members plus the number of support reactions. Here, we have 8 plus 3, or 11 unknowns.
Okay. You can this is the mool mantra, or you can say this is the condition where you can find the conditions for the stability of stresses. Okay, so you have to find a number of equilibrium equations and number of unknown forces in the structure. So how will you find the number of equilibrium equations? If you double the number of joints, you will get the number of equations. Okay, here joints are 1, 2, 3, 4, 5, 6. So there are 6 joints. So your equations will be 2 into 6, 12. So there will be 12 equations. Now, number of unknowns. How can you find number of unknowns? Number of members plus number of support reactions. So how many numbers? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 members plus support reactions. Your roller support will give your single reactions and your pin support will give you 2 reactions. So total will be 3 reactions. So you can clearly see that your equilibrium equations is more compared to your unknowns. So this truss will be unstable.
Since the number
Right,
of
because number of
equations
equations are
turns
more
out to be greater than the number of
comparison to the number
unknowns,
of unknown
then we
forces.
conclude that the truss is unstable. This counting technique, however,
So
does
your
not
truss
work
will be
in all
unstable.
cases. For example, consider this structure. The truss has 8 joints and 13 members. Therefore, the number of equations equals 2 times 8, or 16, and the number of unknowns equals 13 plus
So your
3,
equations will
or
be
16.
again, see, you can see there are 8 joints, so it will be twice into 18. So I got my equations will be 16 and number of unknowns will be members plus your support reaction, so it will be 16.
Clearly here, the
So
number of
both are
equations
equal.
does not exceed the number of
Your
unknowns,
number of
yet
equations
the
and number of
structure
unknowns
is
are both
unstable.
equal. You will get this
Why?
kind of situations where
Because it
your
can be
number of
shown that
equations and
under
unknowns will
certain
be
loading
equal.
pattern, the
So then
static
also it will be
equilibrium of the
unstable
structure
truss.
cannot be
Okay,
maintained.
when your
How?
number of equations plus
Suppose we
number of
place
unknowns
a
will be
non-zero downward
equal.
load of P at the midpoint of the bottom chord of the truss. This makes the vertical reaction at the left and the right ends of the truss equal P over 2. Now suppose we conceptually cut the truss along a vertical plane as shown. Then we draw the free body diagram of each segment. We know that for the structure to be in equilibrium, the equilibrium equations must be satisfied for each segment. One of the equations, however, cannot be satisfied for either segment. Sum of the forces in the y direction is not zero. For the left segment, we have sum of the forces in the y direction equals p over 2. For the right segment, we have sum of the forces in the y direction
Sorry.
equals p over 2 minus p, or negative p over 2. Since p is not zero, the segments are not in equilibrium. This means the structure is unstable. As you can see here, determining the
This is
internal
also a way
stability
you
of
can find out
trusses
the
may
stability
not
and
be a
unstability
simple
of the
task.
structure.
It may involve careful inspection of the geometry of the structure. Generally speaking, if the geometry of a truss consists entirely of simple triangles like this, then the structure is considered stable. Otherwise, the structure needs to be carefully inspected for geometric patterns that are inherently unstable. Here is one such pattern. Any truss structure that embodies this rectangular pattern is considered unstable. See if you can figure out which of the following trusses are unstable. In this session, I'm going to talk about stability of structures.
From which point you were not able to see? I'm playing from here, okay? So that was about the stability of the structure, beam, frame or trusses. Okay. So write your roll numbers in the chat box. All of you write your roll numbers in the chat box. Anyone left to write their roll number? Okay, I'll text in the group, join for the next class. Okay. Okay, roll number 40 was the last. So join for the next class.